Hey everybody, and welcome to the second part of our last statistics lecture. And to get this lecture started, I'd like to use our last example to motivate what we're going to do today. Remember in the last example, we said that the average or mean height of adult American males is 5'10". This is the mean, so this is X bar. The average or mean height of adult American males is 5'10". That's X bar. And the standard deviation is 4 inches. And we call that standard deviation S. And then we had this question. What percentage of adult American males have height between 5'2" and 6'2"? And the first thing that we did was we took this 5'2" and we called it X. We said, let 5'2" be our X. And what we did was we took 5'2" and we wanted to write this height, 5'2", in terms of our mean X bar and in terms of our standard deviation S, so that we could use that empirical rule. And to do that, we said, let's compute X minus X bar. And that will give us 5'2", that's our X, minus X bar, 5'10". And that gives us negative 8 inches. But we didn't stop there. We took this negative 8 inches and we wanted to write it in terms of our standard deviation S. Our standard deviation is 4 inches. What is negative 8 inches in relation to 4 inches? Isn't that negative 2 times 4 inches? And that means it's negative 2 times S. And we did a recap. We said, this is what we just found out. We found out that X minus X bar is equal to negative 2S, negative 2 standard deviations. And then in the next line, we said, we can write this in terms of X. X equals something. And that's what we did. We added the mean to both sides. So we found out that X was equal to our mean minus 2 standard deviations. 5'2" inches is equal to our mean minus 2 standard deviations. And the reason that we did this was because we wanted to write this particular height, the lower end of our range that we're studying. We wanted to write this in terms of mean and standard deviation so that we can use the empirical rule. So 5'2", that's X bar minus 2 standard deviations. And you know what we did after that? We did the same thing with the upper limit of our range here, 6'2". we said, let's call this x, and we'll rewrite this value in terms of our mean and our standard deviation. And we took x and we subtracted x bar, the mean. X is 6'2". The mean is still 5'10". And let's see, starting at 5'10", if we go another 2 inches, we get to 6 feet. And if we go another 2 inches after that, we go to 6'2". So the difference is 4 inches. And 4 inches, what is that in terms of our standard deviation? That's one standard deviation, isn't it? That's S. And I'll write that as 1 times S. What we established here is that with this new x value, 6'2", x minus x bar is equal to 1 standard deviation. And then, just like we did in the case with the lower limit of our range, we rewrote x in terms of the mean and standard deviation. So we added the mean to both sides, and we found out that our new value of x, 6'2", is equal to the mean plus 1 standard deviation. So in order to apply the empirical rule and determine the percentage of adult American men whose heights are between 5'2" and 6'2", we had to take these two heights, 5'2" and 6'2", and write them in terms of the mean and the standard deviation. We did that for both values. And any time that we have a normal distribution and we're trying to compute the percentage of objects in the population that are between this and that, we have to take the endpoints of our range and convert them into mean minus a certain number of standard deviations. Anytime we have a normal distribution and we want to know what percentage are between this thing, this number and that number, we take this number and that number and rewrite them into mean plus or minus a certain number of standard deviations. And in our example, we said, okay, 1, 2, 3, 1, 2, 3. Here's the mean. Here's one standard deviation. Here's two standard deviations. And we said this area represents the percentage of people between x minus 2s, I beg your pardon, x bar. This shaded area represents the percentage of men between x bar minus 2s and x bar. Well, what we knew was that the percentage within two standard deviations either way was 68%. So the percentage between the percentage that were between x bar and two standard deviations to the left of x bar would have to be 1/2 of 68%. That's not right, is it? 68%, wasn't it? Was it? What we said was, suppose that we had both of these regions here. Here we are two standard deviations to the left of the mean. Here we're two standard deviations to the right of the mean. And the entire area here is 95%. This represents 95% of the population. But in our example, we said, we're only interested in those men that are two standard deviations to the left of S. So this would be half of 95%, or 47.5%. And we know that 47.5% of all American men are within two standard deviations to the left of the mean. And then we said, well, what about these guys that are one standard deviation to the right? Well, we did the same thing. We took another normal curve. Boy, I better take some art lessons, huh? Oops. We don't want two standard deviations here, do we? We just want one standard deviation. Okay. Give me a couple of tries, I'll get it right. We want this percentage right there. And we knew that the percentage of all American males, or the percentage of any normally distributed population within one standard deviation either way was 68%. Percentage of the population within one standard deviation either way, 68%. And we said, well, we only want those who are one standard deviation past the mean, within one standard deviation of the mean to the right. We don't want what's over here. We only want what's over here, and that's going to be half of this amount. So that'll be half of 68%, which is 34%. And we said, this is what we want. We want this area plus this area. And that gave us 47.5% plus 34%. And holy moly, what was that? 81.5%, I hope. Is that right? I think so. Now, I did all of this because I want to recap basically one thing that we're going to have to do anytime we're working with normal distributions. We have to take our x values and we have to rewrite them in terms of mean and standard deviation. We have to take our x values and write them in terms of mean and standard deviation. And the first thing we do is we subtract the mean from the x value. And then we convert that into a certain number of standard deviations by dividing by the standard deviation. That's going to be the process. Now, why do we need to know this process? Consider the next example. We're not going to work through it. We're going to work far enough through the example to realize, uh-oh, we hit a brick wall and we don't know where to go from here. And that's when we're going to discuss the remedy. Let's take a look at this. Given that the mean height of adult American males is 5 foot 10 inches, with a standard deviation of 4 inches, compute the percentage of adult American males whose height is between 5 foot 8 inches and 6 feet, 0 inches. So far, there really doesn't seem to be any appreciable difference between this example and the one that we just did. Let's work through this a little bit and see where the you-know-what hits the fan, okay? We'll call this X. And what we want to do, we want to write this value of X in terms of the mean, here's our mean, and our standard deviation. We want to take this X value and write it in terms of the mean and the standard deviation so that we can use the empirical rule to solve this problem. So we take X and we subtract the mean from it. And what we get is 5 foot 8 minus the mean 5 foot 10, and that's negative 2 inches. Okay? I need to write that in terms of the standard deviation. 4 inches is S. Negative 2 inches is negative 1/2 of 4 inches. And we could say negative 0.5 times 4 inches, or negative 0.5 s. Summing up what I just did, I write that x minus x bar is equal to negative 0.5, or negative 1/2 s. And then to write this in terms of x, I'll move the x bar to the other side. X equals x bar minus 0.5 s. And what was x? X was 5'8". And now I'm going to do exactly the same thing for this value. I'm going to call the upper limit of my range x, and I'm going to write this x value in terms of the mean and the standard deviation, just like I did that value. And to start off, I subtract the mean from x. X is, does that look better? X is 6'0". And I subtract the mean, which is 5'10". And I get positive 2 inches. And I want to write this in terms of the standard deviation, 4 inches. What is 2 inches in relation to 4 inches? Isn't 2 inches 1/2 of 4 inches? So that's what I'll write. 1/2 of 4 inches, or 1/2 s, or 0.5 s. And I recap my results. X minus x bar is equal to 0.5 s. And to get my x value, 6 feet, in terms of the mean and the standard deviation, I'll move x bar to the other side. X equals x bar plus 0.5 s. And in this case, what was x? It was 6 feet 0 inches. I guess everything looks pretty good. I still don't see that I'm about to run into a brick wall. But I want to find out the percentage of American men whose heights are between 5'8" and 6'0". That is, I want to find the percentage of American men whose heights are between the mean minus 0.5 s and the mean plus 0.5s. So I'll just draw the graph of my, what is it, a normal distribution? Yeah. I'll draw my normal distribution. And here's x bar. Here's one standard deviation, two standard deviations. Okay. And essentially what I want is the percentage of American men within 1/2 of a standard deviation either way. This is the region whose area I want. And you know what? I find out that what I'm looking for is the percentage of American males whose heights are within 1/2 of a standard deviation either way from the mean. And the empirical rule doesn't tell me that. The empirical rule gives me the approximate percentage that are within one standard deviation of the mean either way. It gives me the approximate percentage that are within two standard deviations of the mean either way. And it gives me the percentage that are within three standard deviations of the mean either way. But the empirical rule doesn't say anything about what percentage are within 1/2 of a standard deviation either way. And now I find out that I'm up that creek of proverb and legend without a paddle. The empirical rule can't help me here. So for situations like this, statisticians and mathematicians have very kindly created what are known as standard normal tables. And essentially, what they give us are all the areas and percentages for the mean plus or minus however many standard deviations we want. And with the standard normal table, the mean is always 0, and the standard deviation is always 1. So we have to take our data and reparameterize it so that we are actually looking at data that has a mean of 0 and a standard deviation of 1. And what we've been doing so that we can use the empirical rule, what we've been doing was pretty good, actually. It won't help us with something like this, but with something like this where we use the tables in our book, the standard normal tables, what we've been doing gets us on the right track. The first thing that we did with our x value was we subtracted the mean, and that's excellent. And then what we did was we took the value of our x value minus the mean and wrote it in terms of standard deviations, which is also good. And what we were doing, really, without knowing it, is essentially computing what statisticians call a z-score. This takes our x values and transforms them into a variable z, where that variable has mean of 0 and standard deviation of 1 so that we can use the tables. And in order to transform our x values into z values, essentially we do exactly what we've been doing here. What we've been doing here is good. And now I'm going to talk a little bit about z-scores, taking x values and transforming them into z, the variable z, so that it has a mean of 0, standard deviation of 1. And we can take that z value and use the tables in our book to compute percentages. Not just whole number standard deviations to the right or left of the mean, but even screwball things like this, half a standard deviation, 1/10 of a standard deviation, whatever. If we take our data and do essentially what we're doing here and transform our x value into a z variable, we can use those tables and get the information that we couldn't use or that we couldn't get from our empirical rule. So what we're going to do next is learn how to take x values like this and compute its corresponding value as a z variable so that we can use the tables in our book. Here we go, z-scores. Given an x value taken from a normal population, the corresponding z-score is given by z equals the x value minus the mean over the standard deviation. X minus x bar over s. If you want to remember a formula, remember this one, okay? X minus x bar over s. And just a comment here, converting our x values into z-scores, in effect, transforms the original normal population, whose mean is x bar and whose standard deviation is s, into another normal population, whose mean is 0 and whose standard deviation is 1. So essentially we're taking, when we compute these z-scores, we're taking our original normal population and transforming it into a normal population whose mean is 0 and whose standard deviation is 1. Well, why would we want to do that? And the answer is, we have standard normal tables that give us the percentages of population between the mean and a certain number of standard deviations, or percentage of the population between within a number of standard deviations either way of the mean. And the number of standard deviations doesn't have to be a whole number. In the previous example, we just wanted percentage of the population within half a standard deviation, either way of the mean. And the empirical rule didn't give it to us. But the standard normal tables will give us the percentage of population between this value and that value, between this number of standard deviations of the mean and that number of standard deviations past the mean, where the number of standard deviations doesn't have to be a whole number. The standard normal tables give us percentages for any number of standard deviations, either way of the mean, not just a whole number of standard deviations. And the standard normal tables, they're on page 798 and 799 of our book. These are the tables that we're going to have to use to do meaningful exercises regarding normally distributed populations. Hey everybody, let's get some practice computing z-scores. Given a normally distributed population with mean x bar equal 8.7, standard deviation S equals 2.2, compute the z-scores that correspond to the following x values. Let's look at the first one. X equals 3.31. We use our z-score formula. Do you remember what it is? Z equals x minus x bar over s. Here's our x. X is 3.31. X bar, 8.7. All over S, the standard deviation, 2.2. And if my computations are correct, that gives me a z-score of negative 2.45. Okay, let's do another one. X equals 12.044. We go to our formula. Z equals x minus x bar over s, and we just fill in the blanks. X, 12.044. X bar, 8.7. And S, 2.2. We turn the crank and out pops the answer. If I've done this correctly, my z-score is 1.57. No, 1.52, I think. 1.52. And let's do the last one now. X equals 14.86. We use our formula. Z equals x minus x bar over s. X is 14.86. X bar, 80.7. Standard deviation S is 2.2. We turn the crank and out pops the answer, approximately 2.8. Now that we've had a chance to compute a few z-scores, let's get some practice using the tables on page 798 and 799. Now we're going to get some skill using the tables in the book. There are two of them. This is the first one. It's found on page 798. Table 12.8a. Here's our exercise. Compute the area under the curve that lies to the left of z equal negative 2.34. So we go to our table, and at the far left, there's a column that's headed by z. We go down the z column until we hit negative 2.3, negative 2.3. And to get this digit 4, we have to go over to the column headed by 0.04. This gives us negative 2.3. This column gives us the 4. And we should see in the column headed by 0.4, 0.0096. In the z column, look at the row headed by negative 2.3 and go across that row until we're under the column headed by 0.04. So that will give us negative 2.34. This is the area right here. So what we've done is we've computed this area where z equals negative 2.34. And maybe I should tell you a couple of other things right now. I'll repeat these later, but I'll tell you now for emphasis. The area under the entire curve here, from negative infinity to positive infinity, the area under the entire curve is 1. Also, if we're dealing with z-scores, the percentage of values that lie to the left of this z value, that is negative 2.34, the percentage of values in the population that lie to the left of this z value is equal to the area under the curve. So they could have asked us, compute the percentage of the population that lies to the left of z equals negative 2.34. And we get that percentage by finding this area under the curve. Now, I will repeat this time and time again, but I wanted to throw that out to you early. Let's do some more area problems. Compute the area under this curve that lies to the left of z equals negative 1.85. So this is negative 1.85. We want to find the area that lies to the left. And that's exactly what our table on page 798 gives us. To find this area, we go to the z column on the far left, and we go down the z column until we hit the row that's headed by 1.8. And once we hit the row headed by 1.8, we go across until we reach the column that's headed by 0.05. This row headed by 1.8, together with this column headed by 0.5, gives us the 1.85. And the value that we find in the row headed by 1.8 and the column headed by 0.05 should be 0.0322. And that's the area. Oops, 0.0322. Now suppose they had said this. Find the percentage of the population whose z value lies to the left of z equals negative 1.85. Find the percentage of the population whose z value lies to the left of z equals negative 1.85. How would we find that? We'd do exactly what we did here, because the percentage of the population, or that portion of the population lying to the left of z, is numerically equal to the area under the curve lying to the left of z. So that portion of the population lying to the left of z, that portion of the population with a z-score lying to the left of z, is the same as the area lying to the left of z. Let's do another one. Okay. Find the area under the curve that lies to the left of z equals negative 1.1. Well, you know, in the two examples we had before, there were always 3 digits here. We only have 2 now, negative 1.1. When they tell us that, we're supposed to realize that the 3rd digit is a 0. So we want the area that lies to the left of z equals negative 1.10. And so we go to the z column and go down until we hit the row that's headed by 1.1. And from there we go over to the column that's headed by 0.0. So this will give us negative 1.10. And here the number that we should find is 0.1357. So the area (1357). Compute the area under the curve that lies to the left of z equals negative 0.52. We're computing this area, and z equals negative 0.52. So we go to the z column, and we go down the z column until we hit the row headed by 0.5. And then we go across the row headed by 0.5 until we hit the column that's headed by 0.02. And that will give us negative 0.52. The answer that we should see there is 0.3015. And by the way, hopefully, as I'm doing these on the board, you're following along closely and doing them yourself. Don't just watch me do it, but actually do these things while I'm doing it also, okay? Here the area is going to be 0.3015. And remember, the area under this entire curve from left to right is equal to 1. Remember also what this area represents. This area under the curve represents that portion of the population whose z-scores lie to the left of z. And we have a little bit of a twist here. Compute the area under the curve that lies to the right of z equals positive 1.97. And, I hadn't mentioned this before, but maybe I should. The center of the graph, horizontally speaking, is z equals 0. So anything to the right of center, anything to the right of center on the graph corresponds to a positive z-score. Anything to the left of center on the z-graph, anything to the left of center on this graph corresponds to a negative z-score. They want us to find the area under the curve that lies to the right of z equals positive 1.9. Well, on page 798, all they have is this graph and the area that lies to the left of this z value. No problem. Remember from the previous lecture, the normal graph is symmetric about the mean. Here the mean is 0, which means that the right side of the graph is the mirror image of the left side of the graph. So the area to the right of z equals positive 1.9 is exactly the same as the area that lies to the left of z equals negative 1.9. So we just go to our table and go down the z column till we hit negative 1.9. And then we go over until we hit 0.07. We go down the z column till we hit the row headed by 1.9. And then we go horizontally across in that row until we hit the column headed by 0.07. And what we should see there is hang on a second. I'm going to have to cheat and look at the book. What the book says is 0.0244. The table in the book says 0.0244. Let me check that again. Yep, that's right. 0.0244. So this area is 0.0244. And statistically, this corresponds to that portion of the population whose z-score lies to the right of 1.9. Let's do another one, kind of like the other one that we did. Compute the area under the curve that lies to the right of z equals 0.65. So here's z equals 0.65. And remember, all of the positive z values lie to the right of the middle of the graph. All of the positive z values lie to the right of 0. The center of the graph is z equals 0. The positive z values lie to the right. So we're looking for this area. Our graph and our table on page 798 only give us the area to the left of z values. No problem. Do you remember why? Yep, you do. That's right. The table is symmetrical about the mean of 0, which means that the left side of the table, or rather the left side of the graph, is the mirror image of the right side. So all we need to do to find the area to the right of z equals 0.65 is go over here and find the area to the left of z equals negative 0.65. And we go down the z column until we hit negative 0.6. And when we hit the row headed by negative 0.6, we go to the right until we hit the column headed by 0.05. And that gives us negative 0.65. And what's the z-score that we find there? 0.2578. This area is 0.2578, and that's going to be exactly the same as this area, 0.2578. Well, that's good. Let's do some more. Hey, everybody. We're going to start working with a different table now. Technically, the table on page 798 is the only one that we need. They give us two tables. Maybe they're right. Maybe if we have two tables, things will be a little bit easier. The table on page 799, table 12.8b, is the area that lies to the left of Z, where Z is positive. So this whole shaded area here is the area that we're going to be computing. And notice the difference really between this table and the table that we've been using on page 798 is that the shaded area extends past the middle of the graph. The shaded area extends past 0. For an exercise, let's consider the area under the curve that lies to the left of Z equals 1.52. Okay? So that means that Z here is going to be 1.52. We go to the Z column, the column headed by Z, and we go down until we hit the row that is headed by positive 1.5. And then we go to the right in the row headed by 1.5 until we hit 0.02. That will give us 1.52. And when we look in the row headed by 1.5 and the column headed by 0.02, we should see the number 0.9357. Let's do another one. Compute the area under the curve that lies to the left of Z equals 0.93. And notice again, Z is positive, so the shaded area extends to the right of the center of the graph. It extends to the right of 0, all the way to 0.93. So here's how we find the area. We go to the table on page 799, the one that looks like this, and we go to the column headed by Z until we hit the row headed by 0.9. And once we hit the row headed by 0.9, we go right until we hit the column headed by 0.3. So that gives, the column headed by 0.03. That's going to give us 0.93. And in the row headed by 0.9 and the column headed by 0.03, we should see this number, 0.8238. This is the area under the curve to the left of 0.93. Let's do one more before we start to get tricky. Compute the area under the curve that lies to the left of Z equals 2.35. Again, Z is to the right, Z equals 2.35 is to the right of 0. So we want the graph whose shaded area extends to the right of 0. And using the table on page 799, we go to the column headed by Z and go down until we hit the row that's headed by 2.3. And once we get to the row that's headed by 2.3, we go to the right until we hit the column headed by 0.05. That gives us 2.35. And I didn't look up the value. Oh my goodness. Hang on a minute. That should be 0.9906. Let me check. Yep, that was right. Now here's a killer, but this is actually the kind of exercise that we'll be seeing quite a bit. Compute the area under the curve that lies between negative 1.13 and positive 2.04. That's the shaded area of this graph. But the shaded area of this graph doesn't look like the shaded areas of either of the graphs that we've been looking at. It doesn't look like the shaded area of the graph of the table on page 798. It doesn't look like the shaded area of the graph on page 799. So what on earth are we going to do? The fact of the matter is we're going to have to use both tables, and here's how we do it. Have we figured it out yet? Here's what we have to do. We have to figure out that the area between negative 1.13 and positive 204 is the same as all of the area to the left of 2.04 minus this area to the left of 1.13. And from the table on page 799, this area is going to be equal to 0.9793. And from the table on page 798, this area is going to be equal to 0.1292. And we just subtract this area from that area to get this area. And the area is going to be 0.8501. Okay, here's another one kind of like the last one. And this example and the one we just did are very typical of the kinds of problems that we're going to have to solve using the standard normal tables on page 798 and 799. Compute the area under the curve that lies between negative 2.41 and positive 0.95. So here's the shaded area that we want. Neither table on page 798 or 799 has a shaded region that looks like this. The tables on page 799 correspond to a shaded region looking like this. The tables on page 798 correspond to tables that have graphs that have a shaded region that looks like this. To get the area under this curve, we're going to have to take this area from the left side of the graph to 0.095 and subtract this area from the left side to negative 2.41. And on the table on page 799, and I'll write that here, page 799, we find that the area of this shaded region is 0.8289, where that doesn't look like a 9, does it? This area, 0.8289. And from the table on page 798, the area of this shaded region equals 0.0080. So if we subtract this area from this area, we get this area. And that's going to give us 0.8209. There's our answer. Now maybe we have time for an application or two. Remember at the beginning of the lecture, this was the problem that we got stuck on. The empirical rule didn't apply because we wanted to go half a standard deviation to the right and left of 5'10". And the empirical rule doesn't deal with fractions of a standard deviation. We want to know the portion of adult males whose height is between 5'8" and 6 foot. First thing we're going to compute is the z-scores. (5'8"). And remember how we get it. Z equals x minus x bar over the standard deviation. So let's see, x is 5'8", minus x bar, which is 5'10", all over the standard deviation, which is 4 inches. And let's see, 5'8" minus 5'10" is negative 2 inches over positive 4 inches, which equals negative 1/2 or negative 0.5. Let's do the z-score for 6 feet. Again, we take z equals x minus x bar over s. X is 6 feet 0 inches. And x bar, the mean, 5'10". All over the standard deviation s. Standard deviation is 4 inches. 6 feet minus 5'10" is a positive 2 inches. over a positive 4 inches. That gives us 1/2 or 0.5. So we want the portion of the population between z equals negative 0.5 and z equals positive 0.5. Let's draw that out. Okay, we got our z-scores. We want the portion of the population between z equals negative 0.5 and z equals positive 0.5. That's the area of this shaded region right here. The graph on 798 doesn't pertain to a shaded region like this, nor does the table on page 799. So what we have to do is we have to take this shaded region from the left side of the graph to 0.5 and subtract from it this shaded region from the left side of the graph to negative 0.5. And let's see, this we get from page 799. This we get from page 798. The area to the left of positive 0.5 is going to be area equals 0.6195, I hope. And the area here is going to be 0.3085. And when we subtract one from the other, we get 0.3830. So this is the portion of the population. And if we turn it into a percentage, 38.3%. So 38.3% of adult American males have heights between 5'8" and 5'10". Maybe we'll do one more like this. What percentage of adult American males have height greater than or equal to 6 feet 5 inches? We're going to keep the mean of 5 foot 10 inches and the standard deviation of 4 inches. But to wrestle with this problem, we're going to have to convert this into a z-score. Our x value is 6 feet 5 inches. And remember, the z-score is x minus x bar over s. X will be 6 feet 5 inches minus x bar, 5 feet 10 inches, all over s, the standard deviation of 4 inches. 6 foot 5 minus 5 foot 10 is 7 inches over 4 inches. And that's going to be 1.75. Z equals 1.75. And we want the percentage greater than or equal to 6 feet 5 inches. And that means we want the percentage greater than or equal to z equals 1.75. So let's see what that looks like. We want the percentage of the population whose z-score is greater than or equal to z equal 1.75. Well, here's the shaded region that corresponds to z equal 1.75. Neither of our tables on page 798 or 799 have a graph with a shaded region like this, but the table on page 798 has a graph with a shaded region that looks like this. And this is just the mirror image of that. We can get this by symmetry. The area greater than positive 1.75 is exactly the same as the area less than negative 1.75. And from our table on page 798, the area equals 0.0401. And we wanted a percentage whose heights are greater than or equal to 6 feet 5 inches. Just take this and multiply it by 100, and we're going to get 4.01%. Not too many guys greater than a height greater than 6'5", and that definitely includes me. I'm nowhere near 6'5". Well, I think this will conclude our lecture. We've seen enough about normal tables and z-scores and a few applications to be able to work what's in the book.